So yeah, so today we will see the second course of the deep learning specialization, and which is, so here we were discussing the deep learning specialization from summarized notes by by this user on GitHub. So today we will try to cover as much as possible. Like, are there any questions, any doubts in the from the previous class that you guys want to discuss, or is there anything that you are trying for your projects or the term paper that you want to discuss? Yes, no. Okay. So this is about improving deep neural networks, hyperparameter tuning, regularization, and optimization. So the course, basically, we have the summary here, and it tells us about how to get deep learning work well. It's not just about knowing how what is there in the model. So you should also know how to make things work well for you. And so rather than considering it as a black box, you should understand what drives performance, how to get good results. So the first concept is about the training, dev and test sets. So if you have any data set on which you are trying to build a model, a statistical model, which can be using deep learning or any other machine learning project. So the first thing is you divide your data set into training, dev, and test. So people would typically call the second half as dev, or some others might call it validation data set. So typically it is 60% training, 20% validation or dev, and 20% testing. So you would train your model on the 60% of the data set, and while training, you would evaluate the performance of the model on the 20% data set from the entire data. So, but this 20% the model has not seen, the model is not getting optimized due to this 20%. And after the training is complete, you would evaluate the model on the remaining 20% of the data set, which is known as the test data set. So these numbers are not hard coded. You can change them depending upon the problem, or you can use them as you wish. So the basically the way to go ahead with any project is that you have the idea, and then you code it and you experiment on different things. So there are, as we were discussing in the last class, there are a set of hyperparameters in any deep learning project. So you would need to tune the hyperparameters, and it's very difficult to get all the hyperparameters right for a new application for the first time, and you would have to loop through many times to figure out the hyperparameters. And so the data set, yeah, so as we were discussing, it would split in three parts, and you will try to build a model using upon training set, and then try to optimize the hyperparameters on the dev set as much as possible. So the loss function is getting optimized on the performance that the model is showing at the training time on the dev set. And then after your model is ready, you try and evaluate the testing set. So this is the trend of so they say that if the data set is these are the number of samples of the order of from 100 to maybe 10 to the power 7. So you do 60, 20, 20. And if your data set is huge, like from 10 to the power 7 to infinity, you can even do a 98, 1, 1, because then 1% of the data that you are not, or the 2% of the data that you are not showing to the model, that the number of samples in that becomes huge. So the the trend these days is to give the training data and the biggest largest amount of training data, because these are data driven models, so you need as much amount of training data as possible. And so you have to make sure that the validation or the dev set and test set, they are coming from the same distribution. So they are, it's you should not typically use the a different data set for validation and a different data set for testing. For example, if cat training pictures is from the web and dev or test pictures are from user's cell phone, so they will have a mismatch, and it is better to make sure that the dev and test sets are from the same distribution. So basically all the training, the dev set, the test sets, it should be from the same distribution. And it is okay to only have a dev set without a testing set, but a lot of people in this case call the dev set. So you would see people just talk about training data and testing data. They would not talk much about the dev or the validation data set. But so it is it is it is it should be used, and that's a good practice to use the dev set. And so next comes the concept of bias versus variance, and these the techniques to learn bias. So this this figure, it should be, you should remember it by heart. Like it should come to your mind whenever somebody talks about bias and variance. So people would typically talk about bias variance trade-off. So you can see that uh, we have a data set on the leftmost side. So it's a classification problem, and you can see that we have the cross and we have the circles, and the line here represents our model. So all on the left are a particular class. In this case it looks like class 0, and all on the right are the class 2, which is looking like the cross. So this is high bias. So what do we mean by high bias is that the model has a large error. As you can see that a number of crosses, they 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 end up in the region, or the model is classifying them as circles. So these ones, this one and these ones. And then we also have this circle which the model is classifying as a cross. Now you can also have high variance, which is the rightmost plot. So uh, this is a model which is a very complex polynomial, and you have tried to. So this is in the training data set. You have, so this is when we are talking about this bias variance trade-off. The line here represents the model, and then so you can see that in the training data set, our model has perfectly captured all the classes. So whatever is a circle is a circle, whatever is a cross is a cross. But then think about it, will this model generalize? So if you would test this model on a, if you would use this model on a test set, this model will perform really bad. And this is the result of overfitting. So we say that the model is overfitting, and this problem is known as high variance. We have to find out an optimum solution in which we are minimizing the bias and minimizing the variance. So that is known as the bias variance trade-off. And we have to find a model, something which is just right. So which is not too bad, and which is also not overfitting. So if your model is underfitting, it has high bias. If your model is overfitting, it has high variance. And your model will be all right if you balance the bias and variance trade-off. So if you, so yeah, so another idea to get bias or variance if you don't have a 2D plotting mechanism, so you can check your the error that corresponds to your training data and your dev error. Okay, so dev is something that the model has not seen, but on which the model is trying to minimize the loss. So if your training data set has a very low error and your dev data has a high error, what does that basically mean? So in this case, your training data will be having a very low error, okay? But your dev set, it will have a high error. So that basically means that the model is overfitting. So you can compute these. So he's saying that you cannot always plot these kind of 2D uh, 2D figures. So how to test whether your model is underfitting, overfitting, or how to perform the bias variance trade-off? Now, if your training error is more and your dev error is less, so that basically corresponds to this. So this is, in this case, it is model is basically showing high bias in your training data, and but it is still better than the, in this case, so than the high variance. So you can see this is example of high bias, where the model is underfitting. And the best case scenario is that your training error also comes down and your test error also, so it comes down along with the training error. So that is the ideal case scenario. So there are some recipes that he recommends for machine learning. Now if your model has a high bias, so basically on the training data the model is showing a high error, then try to make the neural network bigger. You basically try to increase the complexity of your model. So increase the number of size of the hidden units, the number of layers. Next, you can try a different model that is suitable to your data. So you can maybe try a unit, or you can try an R. So different models for different applications. You can try a different, altogether a
Sir,
different model. You can run it longer. So you can basically run more epochs of the model. You can train it for
Sir,
longer.
the slides are not
And you
visible,
can
sir.
also use different or advanced optimization algorithms. So these
Hello,
are the recipes for high
hello.
bias. And then you have, if to solve the problem of high variance. So understand that in when your model has high variance, it is basically overfitting to the data, or it is giving very good performance on the training data, but it is performing really bad on the test or dev set. So one solution can be to get more data, and
Hello,
then
sir.
you can try something known as regularization. So regularization is something which
Hello, sir.
reduces the complexity of your model, or which penalizes the large models. And you can also try a different model that is suitable for your data.
Hello, sir.
So you should try the these two things as a priority if you have
Hello.
until you have low bias and low variance. So our ultimate goal is that the bias or the error should be less, and the model should also not underfit. The model also should not
Sir,
be like it's performing, it should generalize. So it should not be performing, it should not be like it's performing really good on the training data but bad on the dev or the test set. So that's what he says, like in the older days there was this bias and variance trade-off, but because now you have more options or tools, it's really helpful to use deep learning. And it never hurts to basically train a bigger bigger neural network. Now we're talking about regularization, so we'll see what it is. If you guys can remember, we were talking about ridge regression, lasso regression. So basically, ridge regression and lasso regression were were a different form of regression wherein we changed the loss function by adding some number to the loss function. So we were basically penalizing the high number of precursors or the large number of weights or the weights in the multivariate linear regression. Is there a question that you guys have?
Yes, sir.
I can't.
Yes, sir.
Yeah. Okay. Yeah. I can hear you now.
Okay, so sir, actually there was a lag when you were explaining this whole thing, and
Okay.
it was not moving, sir.
Okay. The screen was not moving.
Yes, sir.
For me,
So
it is,
is it moving now?
I'm not getting issue from my side here.
Yeah, yes, sir. Cursor is moving. Yes.
Okay. So the things were moving for most of you when I was explaining.
Yes, for me it was yes.
Okay. So maybe for the people for whom it's not, maybe you can reconnect again and maybe you see if it gets resolved. Is that fine?
Yes, sir.
Yeah. Is there any question in the chat
Yes,
box?
sir.
Yeah.
Sir, I have one question.
Yeah. Please go ahead.
Sir, what Dave error is indicating and how it is different from training error and testing error?
Okay. So you see, you have 100 samples, let's say. Okay. You have 100 training examples. Now, what you will do is you will basically divide that data into you can divide it into 60, 20, 20. Now you will only train the model on the 60 samples. Okay. That is your train set. The rest of the two groups are looks like, so the first one is known as the dev set, the second one is known as the test set. So for now you forget about the test set, okay, and we will only consider the training and the dev set. So what you do is you train the model on the training set, okay, but at the end of the epoch you also compute the loss on your dev set. So you try to minimize the loss on the dev set, so the model is not getting trained with the data in the dev set, but at the training time it is following or it is taking cues from the from the loss or the from the error that the so or how the model is performing on the dev set. Is that clear? Or
Yes, sir.
okay, so anybody else has any other question? Okay, I suppose no. So yeah, where were we? We were at regularization. So basically adding regularization to the neural network, it helps reduce okay. So high variance basically means that the model is overfitting. So how would you basically reduce overfitting? So you would add regularization term to the loss function. So what we typically do is, so we would say that, okay, so there are two types of distance measures. One is L1 norm, then we have another one is L2 norm. So L1 norm is the modulus of so basically when you are computing the distances, that time these two norms are introduced. But for our case, so L1 norm is you sum over all the weights in the model, but you sum over all the absolute values of the weights. Okay, so you remove all the negative terms. L2 norm is you sum over all the square of all the weights. So that's what your L2 norm is. Now, how would you introduce regularization? So what we would typically do is, so you can see that we have this j as the cost function. So this was our cost function previously without regularization. So we would say the original cost function plus lambda divided by 2m. So lambda is our regularization parameter. Now this is another hyperparameter. You can train on this on different values of this hyperparameter also. And you see we have multiplied lambda divided by 2m, where m is the number of samples into sum of w square, or if it is an L1 norm, then you say sum of modulus of w. So what are you doing here? You are basically increasing the cost. You are increasing the value of the loss function if there are more weights in the network. So if when will you have more weights in the network? When your model size will increase, the number of layers will increase, or the number of neurons per layer will increase. That is the time when your number of parameters or your number of weights will increase. So you are basically penalizing on that, and you are trying to make some kind of balance between a deep neural network and also ensuring that you don't end up overfitting the model, overfitting on the training data. So this is the fundamental concept of regularization. And he says that L1 regularization version makes a lot of w values become 0, which makes the model size smaller. But L2 regularization is something which is most commonly used. Now lambda here is the regularization parameter. We also call it as the hyperparameter. So this is our another hyperparameter. So you can see that as we are discussing more on the concepts, we are adding more on the hyperparameters. So okay, so now we we can see that we already seen the so the normal cost function, the way it looks like, the L2 regularized version of the cost function, and the L1 regularized way of the cost function. So okay, you would then typically do back propagation, and you would train the model using different algorithms. So most common or popular one is gradient descent. So you would compute the gradients of the cost with respect to the weights, and then you would update the weight in the weights in of your model. So it says that in practice, this penalizes large weights and effectively limits the freedom in your model. Now, why regularization reduces overfitting? So there are two intuitions that he offers. Intuition one is, if lambda is too large, a lot of w's will be close to zeros, which will make the neural network simpler. So these so basically if you are increasing the value of your lambda, you're cutting down on your model, or you are increasing the cost, or you are penalizing large model. And if your lambda is good enough, it would just reduce some weights, and that basically make the neural network overfit. And the intuition too is that if lambda is too large, w's will be small or close to zero, and model will use the linear part of the activation function. So we will go from non-linear activation to roughly linear, which would make the neural network a roughly linear classifier. And if it should be good enough to so that there is a balance, and the weights are, so the model does not become too simplistic, and we are also avoiding overfitting. Then there is an implementation tip. If you implement gradient descent, one of the steps to debug gradient descent is to plot the cost function j as a function of the number of iterations of gradient descent. So yeah, this is very commonly used, and you would typically plot the cost function to see whether j is increasing monotonically after each iteration or each epoch. And if you plot the so 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 if you plot the no regularization version, then you might not see it decrease monotonically. So that is an implementation tip for regularization, to check whether your regularization is working or not, and whether it has any effect or not. So then there is another type of regularization. It is known as dropout regularization. Now, what happens in dropout regularization is you would eliminate some neurons or weights on each iterations based on probability. So you would, yeah, just is everybody able to see my screen?
Yes, sir.
Hello?
Yes, sir.
Yes, sir.
No issues, right?
Yes, sir. Yes.
Okay. Okay. So the dropout regularization, what it would typically do is it would eliminate, so it would randomly switch off some of your neurons or some of the nodes in your deep neural network, and that is known as the dropout regularization. So for example, so the most common technique he talks about is inverted dropout. And for example, you say that keep probability is 0.8, so you would basically keep only 80% of the neurons, and the layer for which you want this to work, so you say that this is for the layer number 3. And this basically means that 80% of the neurons will stay, the 20% will be dropped. And so this one, so you can see that randomly at every epoch you would switch off 20% of the nodes. So you can see from here. So if you would generate a random number, so between the layer, so it's saying it's for layer 2 and for layer 3, this is for layer 3. So the weights of the weight matrix, it's a 2D weight matrix. So the activation values are AL, and shape, so it has got a shape of 2, total shape of 2. So in Python we start with 0, so we have 0 and 1. So we would just randomly see that we would randomly generate a 2D matrix of size same as the number of weights. And we would say that, okay, if the value of those random numbers is less than zero point 0.8, then you just keep only then. Otherwise, if it is greater than zero point 0.8, so if you would generate a random number, you would get numbers between 0 and 1. So all the weights above that, you just switch them off. So this will be a boolean, and if you multiply this boolean with the layer number 3, this would only keep the neurons, or this would only keep the the weights which are like which are in that 80% threshold. So one important thing to note is, at the test time, we won't use dropout. So if you do implement dropout at test time, that would add noise to your predictions. So this is a very effective strategy to perform regularization. And as we would see that it is even used in state of the art models such as wavenet. And yeah, okay, so it is it is used in models like attention. So we would discuss about those models, but these are about the basics of regularization. Then he talks about understanding the dropout. So we talked about the intuition was that dropout randomly knocks out units in your network. So it's as if on every iteration you are working with a smaller neural network. And so using a smaller neural network, it should have a regularizing effect. And then another intuition is that you can't rely on only one feature, so you have to spread out your weights. So randomly switching off the weights in a deep neural network, you would have to you would be basically, what you would be doing is spreading out the weights, and not just, it's not just one feature which is playing a role in deciding deciding the model, or the weights of the model. So it is possible to show that dropout has a similar effect as L2 regularization, and you can have different keep prob for each layer, and the input layer dropout has to be near 1. So you would basically, so if you keep value of 0.5 for the for keep prob at the input layer, that would basically mean that you are turning off your input features themselves. So you wouldn't want to do that. So that is something which is very important. So for the input layer, you would typically want to keep it near 1. And if you are worried about some layers overfitting than others, you can keep you can set a lower keep prob for some layers than others. So if the layers which are overfitting, you can keep a low value for those layers. And if they are not, if they are not overfitting, then you can keep use a higher value. So another alternative might be to have some layers where you apply dropout and some layers where you don't, and then you just have one hyperparameter. So this key prob is your another hyperparameter that you can tune, and you can use different values, and you can come at some conclusion as to what is the optimum value of this key prob hyperparameter. And a lot of researchers with the computer vision community, so most of our algorithms that we would use for spatial datasets will be from the computer vision. So they use dropout because the input, they have a very big input size and almost never have enough data. So overfitting is a very common problem. And dropout is it's a regularization technique to prevent overfitting. Now, a downside of dropout is that the cost function is not well defined and it will be hard to debug. So your cost function will have the different W's. So it will be basically y minus y hat square, and then you sum over it, divide by 2m. So you're all at each epoch or at each iteration, the W's that would be considered or the weights that would be considered would keep changing. So you wouldn't have a constant definition of your cost function. So to solve that, you would need to turn off dropout if you want to debug the cost function and or plot j with iteration. So on y-axis you would plot the cost function, on x-axis you would plot iterations, and you have to set the key prop to 1 and run the code and check if your model is training or not. Then there are other methods to do regularization. One of them is known as data augmentation. So this one we can actively use in our community. So in the computer vision, what people would do is they would flip the images horizontally. So you can flip them horizontally, or you can rotate them randomly to get more data. This is very commonly used in optical character recognition. So optical character recognition is if you have an image of a text, so your model should be able to tell what are the characters in that image. So that is optical character recognition, and it works really well. You can impose random rotations or distortions to the original data set. And new data obtained using this technique isn't as good as the real independent data. So, but still, it can be used as a regularization technique. Now, another method which is very popular these days is known as early stopping. So you can see that in this graph, you can see the blue curve. So the blue curve corresponds to the training error. On x-axis you have the iterations, on y-axis you have the cost function. The purple one is the dev set error. So that is a sample, or that is a group of data on which you are not training the model. So there will be a point, so it would while you are training the model, so it would converge or it would reduce with by increasing the iterations, just like the training error, but it would be only until a certain point, after which your dev set error will start rising. So that means basically beyond this number of iterations, your model has started overfitting. So you would typically use something known as early stopping. So you would not train beyond this point. That is what we mean by early stopping. And we plot the training and the dev set together. At some iteration, dev set cost will stop decreasing, uh, and it will rather start increasing. We will pick a point at which the training set error and dev set error are the best. That is the lowest training cost with the lowest dev cost, and we will take these parameters as the best parameters. So yeah, so Andrew prefers L2 regularization instead of early stopping, but early stopping is showing really good results these days, with a lot of different works that are coming out. And its advantage is that you don't need to search a hyperparameter like lambda in L2 regularization. So you can just stop at a particular number of iterations and that's it. Then another method to do regularization is to use model ensembles. So the first can be you can use, so by ensembles what we mean is you take there are different methods of doing ensembles, like we were seeing in the first class. So I will, if I can just maybe go to that model ensembles. Yeah. So we had this, if you remember, we had this cheat sheet on the different types of ensemble learning in machine learning. So you can have bagging, you can have boosting. So bagging is train n different weak models. So all the n models are different. You train them on n overlapping subset of input data sets in parallel. So you divide your input data set in n different groups, and train n different models on those n different groups in parallel. And in the test phase, each model, you evaluate each model and you see which model gives the best prediction. So according to that, at the test time, you would assign weights to the different models, and that is known as bagging. So it is like you are using all the models parallelly. Boosting is you are doing incremental learning. So you train n different models, but you train them in a sequential order. And stacking is if you would want to stack, so you train n different weak models with one or two of the subsets of the data set in parallel. And once the weak learners are trained, so they are used to train a meta learner. So you basically train n different weak models on similar data set, and using these weak models, you would then assign some weights and to each model, and then you would combine the predictions of all these models to create what is known as a meta learner. And you combine the predictions and carry out the final prediction. So in the test phase, each model predicts its own label, and these labels are then fed to the meta learner, which generates the final prediction. So yeah, so model ensembles is another way of performing regularization. So you can have the different independent models and test time average their results, or use some kind of weights which you can find out from the dev set, and use those weighted average of the models at the test time. And it has generally been seen that it can give you around 2% extra performance. It reduces the generalization errors, and you can use some snapshots of your neural network at the training ensembles and then take the results. So then the next important concept is to normalize your inputs. Now, it's not just your inputs. You should also normalize your target, the variable which is what you are trying to predict. And it's a well-known fact now that if you normalize your input from to the range -1 to 1 or 0 to 1, this basically speeds up the training process. And normalization, basically you can do using mean and variance. So you can say x minus mean divided by variance is a is one type of normalization. You can also have a min max type normalization. And he says that if we don't normalize the inputs, our cost function will be deep and its shape will be inconsistent, or it would be elongated, and then optimizing will take a long time. So if you would want early convergence, then normalization is very important. And if we normalize, the opposite will occur. The shape of the cost function will be consistent, and we can use a larger learning rate. So optimization will be faster. One problem that comes in at the time of training the deep neural networks is known as vanishing gradient or exploding gradients problem. So vanishing gradients basically means, so if you remember in our gradient descent algorithm, so we basically have the way we basically update our weights is W is equal to W minus learning rate multiplied by the contribution of that particular weight to the cost function, or del of j by del of w. So how much of per unit change in that particular weight would lead to a change in the cost function. So this is our gradient descent algorithm. And but sometimes what happens is that this the derivative term, or that will either vanish, or that will tend to go to zero, or it will explode, it will go to infinity. Either of the situations are bad for us, because if this goes to zero, then we won't be able to update our weights. And if this goes to infinity, our weights would go to infinity, and the model that we would have is kind of a junk model, and doesn't make any sense. So these problems occur when your derivatives become small or very large. And to understand this problem, we have to, so suppose he takes the example of a deep neural network with L layers, and all the activation functions, for example, are linear, and each bias term is 0. So if you think in that terminology, then you would just simply be multiplying your input with your weights, weight matrices, and you would get your y. So your y hat, which is what your model has predicted, would be WL. So at L layer, what is your 2D weight matrix, and at L minus 1 up to, so starting from 1 to L, you multiply all the weights and multiply all of them with in the input. And for example, then if you have two hidden units per layer, so and also x1 equal to x2 equal to 1, so you would basically have, so you can so if you have just two hidden units, so for a particular layer, you can have this kind of a weight matrix, 1.5 0 0 1.5. And then what you would typically be doing is you would be multiplying, so you would be multiplying this with the input. So you would be saying 1.5 0 0 1.5, and you would multiply this with x. And if you do this, like if it is similar in all the layers, so 1.5 raised to the power L, this will become very large. And if this is large, then that basically will mean that at the time of performing gradient descent, your weights would start going to negative infinity. Now a similar example, like if you have a term 0.5, so 0.5 raised to the power L, so this will tend to 0, so it will be very small. So this will turn into, so the update term will go to 10 to 0. So this is also bad. That is a vanishing gradient problem. And so the last example explains that the activations and similarly the derivatives will be decreased or increased exponentially as the function of the number of layers. So if your W is greater than the identity matrix, the activation, so identity matrix will have 1 0 0 1. So the activation or the gradient, if it is identity matrix, that means so y hat equal to x. If it is greater than identity matrix, that means you will have an exploding gradients problem. If it is less than the identity matrix, that means then you will have a vanishing gradients problem. Now recently, so this course was around 2018. So this recently is according relative to 2018. And he says that Microsoft trained 152 layers ResNet, which is a really big number. With such a deep neural network, if your activations or gradients increase or decrease exponentially as a function of L, then these values could really get really big or really small. And this makes training difficult, especially if your gradients are exponentially smaller than L. Then gradient descent will take tiny little steps. So if your gradients will get smaller, so your update terms, like, so how the way you're updating is W equal to W minus learning rate into the update term. So if your gradient is very small, then your gradient descent will take tiny little steps to update the weight matrix, and this will take a long time for gradient descent to learn anything. And there is a partial solution that doesn't completely solve the problem but helps a lot. So you carefully choose how you initialize the weights. So that is a very important aspect. So there are different methodologies for initializing initially the way you are assigning weights. So typically people would say that you can do random initialization. So that is what is the next topic. So weight initialization for deep neural networks, and that is considered as a solution for vanishing or exploding gradients problem. So you can have one of the method is known as is basically you what you would typically do is you would randomly initialize the weights. Or what you could do is you can say that you do random initialization, but you multiply it with the square root of 2 divided by number of, so n of L minus 1 plus n of L. So here I think n is the number of neurons in that, so in that layer and in the layer previous to that. So this is following Bengio et al. And then you can also, what you can also do is, so you can just say square root of 2 divided by n minus 1. So number 1 or 2 in the numerator can also be a hyperparameter to tune, and this is one of the best way to partially solve the, so basically he's talking about, so the way you start with with some values of the weights. So what are the typical values at which you will start your training? That matters a lot. So it can solve your vanishing or exploding gradients problem, and won't let your gradients explode or vanish too quickly. So the initialization so this is also known as the He initialization or the Xavier initialization. So it was published in a 2015 paper, and these initializations are very popular. So if your model is not training, so you can use the He and or the Xavier initialization. So I think like they are so if you search for He initialization, so yeah, so this is your He initialization, the one we talked about in the last. So this one is your He initialization, and let us see what is Xavier initialization. So then yeah, so this is the Xavier initialization. So basically, yeah, this one, if you add with the number of nodes in the or the number of neurons in the ith layer and in the next layer or in the previous layer, so that is known as the Xavier initialization. So then comes the so how would you, so there are methods to basically, so to approximate the gradients and to, which tells you if the implementation of your backpropagation is correct or not. And you would typically do a numerical calculation to back calculate the derivatives. So this is a check people used to use it when you would typically write everything from scratch. But I think yeah, with our we are focusing more on applied AI, so it would, so your back propagation would work, definitely work if you are using TensorFlow or PyTorch. And yeah, so we have already discussed the initialization. So this is a summary of that, and the regularization. So we can use L2 regularization, L1 regularization, dropout, and then comes the optimization algorithms. So there are three different types of optimization algorithms. So one is known as the batch gradient descent. So in batch gradient descent, you would run gradient descent on the entire data set. So you would not so that is something you would do in the mini batch. In the mini batch gradient descent, you would basically divide your data into a lot of different mini batches, and that is known as mini batch gradient descent. And then there is another optimization algorithm which is known as the stochastic gradient descent. In stochastic gradient descent, you would typically use just one sample at each iteration. So you would have different iterations and you would use only one sample. So the thing is, if you plot the cost function for batch gradient descent, so in batch gradient descent, we are using all the samples at every iteration. You would get a smooth cost function, but the training would be much slower. Now, in a mini batch gradient descent, you would get this kind of a cost function, which is somewhat looking like wavy, but it would converge faster than the batch gradient descent. So batch gradient descent basically takes too long for one iteration, because it is you're optimizing on all the samples, whereas stochastic gradient descent, it is too noisy, because you are just taking one sample at a time. Mini batch gradient descent is something which is in between batch gradient descent and stochastic gradient descent, and it is faster. You have vectorized advantage. You can make progress in a faster manner, and doesn't have to always converge. So the size of the mini batch is also a hyperparameter. Uh, so that is a very important parameter in the while tuning your model. Then you would be aware of the concept of exponential weighted averages. So let's say, for example, so we'll discuss why we are talking about this. So if you have some numbers from so if you have 180 numbers, and those numbers are 40, 49, 45, and the last number is 60. So you can create weighted averages of these numbers. So you can say that, for example, v0 is 0, v1 is zero point 0.9 into v0 plus zero point 0.1 into t1, and then so v2 is zero point 0.9 into v1 plus zero point 0.1 into t2. So here 0 point 0.9 and 0 point 0.1, these are the hyper parameters. So the general equation then turns out to be, so rather than having these t's, what you are eventually having are these v's, and the way to compute these v's are beta into v t minus 1 plus 1 minus beta into theta of t. So theta is so you can use the different values of beta. So beta equal to 0.9, it will average the last 10 entries. The beta is 0.98, it will average the last 50 entries, and beta is 0.5, it will average the last 2 entries. So the best values that are recommended are between zero point 0.9 and 0.98. And what he's recommending is that so you can see for the mini batch gradient descent, your cost is basically having some kind of spikes. So you use this kind of an exponentially weighted average methodology over your cost function while using mini batch gradient descent. If you use that would basically make your cost function smooth, because you would be taking an average of last few numbers depending on the value of beta, rather than just taking a particular value of that cost function. So the intuition for this is, like, the reason why exponential weighted averages are useful for further optimizing gradient descent algorithm is that it can give different weights to the recent data points, and based on the value of beta, if beta is high, it smoothens out the averages of skewed data points, or which is the oscillation, and it reduces the oscillations in the gradient descent, making the training faster and smoother. You can move over to the minima in a faster manner. And so yeah, there is some understanding of the exponential weighted averages. And yeah, so this is, so when you use this kind of a methodology over your the way you would, so this is what you would apply on while updating your weights. So you would say that so this is your gradient terms, or how much, so del j by del w, how much you should change in your weights. So you would apply this beta term to that. So you would say beta into the gradient plus 1 minus beta into del of into dw. So similarly you would say over the bias term, and then you would use the gradient descent to update the weights. So if you do that, then you are basically minimizing on the oscillations, and this term beta is known as the momentum term. So if you would come across some article which says that we have used momentum at the time of training, this is the hyperparameter that they're talking about. So while using mini batch gradient descent, they are using momentum to smoothen out the cost function, which can become, or which can become abrupt, or which can have some kind of oscillation, large oscillations. And then so this is about the momentum term. And then we have the different optimization algorithms. So one of them is called the RMS prop. So RMS prop is, so I have taken out this material for RMS prop. So in RMS prop, what you would typically do is you would look at the sign of the last two gradients for updating the weights. If they have the same sign, that means we are going in the right direction. So if the weight, if the gradient, both of them are having a positive sign, that means the weights are to be increased. Sorry, that means basically the weights are to be decreased, because gradient descent says W equal to W minus alpha into the gradient term. And if the signs are in the opposite direction, so that means we are going wrong. So if they have the same sign, that means we are going in the right direction, and we should accelerate with a small fraction, meaning that we should increase the step size. You can increase the learning rate. And if they are different, that means we did a too large of a step. So we basically jumped a higher step on the cost function, and we should decrease the step size by some factor, let's say 0.5. And so then you limit the step size between those two values, and these values really depend on your application data set, and good values can be for default are so 50 and a millionth, so whatever. And then you can do the weight update. So this algorithm is known as RMS prop. And then we have another algorithm which is known as the Adam algorithm, so which stands for adaptive moment estimation. Now adaptive moment estimation, or Adam, is a very popular optimization algorithm. What you typically do in Adam is you would combine RMS prop and momentum together. So you would also have momentum term, you would also have the RMS prop algorithm, wherein you would see the gradients of which would update the weights if two consecutive gradients are having same sign. You would basically increase the step size. If they are having a lower sign, opposite sign, you would decrease the step size. So if you would combine both RMS prop and the momentum, then basically you would what you would get is the Adam optimization algorithm. And the hyperparameters that you would be needing for Adam optimization are learning rate. So, and then beta 1 is for momentum. And then you have another parameter beta 2, which is a parameter of the RMS prop algorithm. And then you would have a parameter epsilon, which is generally kept as 10 to the power of -8. Now another important concept is of the learning rate decay. So it is basically, if you are increasing the number of epochs or iterations, you would basically reduce the your learning rate. So you can think of this as if you are going down your cost function. So near the minima, you would not want to take a large step size. So you would want to take a smaller step size. So that is why you would basically need the learning rate decay. And so after seeing all these after seeing this course, the material from this course, we can see that there are a lot of different hyperparameters that we need to tune. So we have the learning rate, momentum, mini batch size, number of hidden units, number of layers, learning rate decay, regularization lambda, the activation functions, the Adam optimizer, the beta 1, beta 2, epsilon for the Adam optimizer. And then you can so these are, it is hard to decide these hyperparameters. So you would have to tune to your on your data. And there are different methods of tuning also. So one is known as the grid search, Then we have the random search. So we already discussed these two methods, the grid search and the random search. If I will see if I can pull that out from one of the cheat sheets. So I think it was in the scikit-learn, yeah. So you can, yeah, you can see here. So the in grid search, like we discussed in the first initial classes, so you would basically have a grid of all the possible values of the hyperparameters, and you would compute the cost function over that large grid. Whereas in the randomized search, so you would randomly search for different values of your hyperparameters. Typically, a good method is to use higher randomized search and then reach a value, and then around that the particular combination of the different hyperparameters which you have searched using random optimization, you would basically run a grid search and find out even a further tuned model. So there are, yeah, so then you can do various things. I think, yeah, this is, yeah, so then there is this concept of batch normalization. Batch normalization is, so we were talking about normalizing the inputs. In batch normalization, you would also normalize within the layers. So that is known as the batch normalization. And it has been seen that batch normalization is very good for the model, or it is an effective strategy to train your model. And so why does it work is the same reason why we would normalize the inputs, and it reduces the problem of input values shifting. So also it does some kind of regularization. And yeah, so we will see, yeah, so we have another thing which is known as a softmax function. So softmax you can use for regression, or you can use for a classification problem. So typically, if this is your neural network, so these are the final values that you have got: 1.2, 0.9, and 0.4. So what you would typically do is you would compute a sum of all these values. You would say 1.2 plus 0.9 plus 0.4, and then you would compute 1.2 divided by sum, 0.9 divided by sum, 0.4 divided by sum. So you would get these numbers which actually sum to 1. Okay, so this one sums to zero point 0.8 plus 2. Yeah, this one sums to 1. So even in a classification problem, this one helps. This one basically helps to find out which class, or this is basically inherently predicting the probabilities. So this one predicts the which class the model is predicting. So either class 1, 2, or 3. And then you can also use this in at the time of regression. So you can so softmax is a very important layer to know. And then there are different deep learning frameworks. So PyTorch, so there were a lot of them some years ago, but things like Cafe, CNTK, Lesane, MXNet, these ones, Theano, these ones were really popular at the time at in 2015-16. So TensorFlow, PyTorch were not available that time. So these days, the whole deep learning ecosystem is dominated by TensorFlow and PyTorch. In fact, not even TensorFlow now. People are more or less using PyTorch for their for programming. And yeah, he uses some examples of TensorFlow. So this was about the theory session for today. We will see some examples of we will see the tutorials of TensorFlow. We will take a quick 5-minute break here. If you guys have any questions, you can please let me know. Otherwise, we'll start back at 3:15. Am I audible? Is there any question?
Yes, sir.
Yeah.
Sir, I have one question that
Yeah, please.
uh,
Yes.
in the section of exponential weighted averages,
Hmm.
so
Okay. Okay, just a second.
it is uh,
Hmm. Yeah.
it is used for minimizing the oscillations
Yes.
uh, while training, and also
Yes.
it smoothens the oscillations.
Yes.
So my question is, for example, if we are having any data set and we plotted time series for that,
Hmm.
and if it is giving very much oscillations,
Hmm. Okay.
so if we want to compare that plot with some another feature or plot, let's say, which is already smooth,
Hmm.
so can we use this technique to
Yeah,
compare
yeah. You can,
with
so
that?
you can use this in general to smoothen out your data set, to smoothen out any time series as well. Yeah, you can use that.
So is it creating, or while smoothing it is taking the nearest value for reducing that fluctuating
Yeah,
amplitude?
so basically you are, what you are doing is you are starting with so you are in, so you are saying that initially the value of v is 0. Okay. And
Yes.
you are choosing some value of beta. So let's say if you choose beta as zero point 0.9, so then he says that you would be averaging how many last 10 entries. So if you would start with v, the value of v as 0. So first time the value of v1 will be zero point 0.9 into 0 plus zero point 0.1 into the first value. So that will be your v1. So then your first initially some values would not be according to what your actual values are, but after the 10th or 11th number, it will be a weighted, it will be a average of the last, so last numbers or last few entries depending on the value of beta. So if you are choosing beta as zero point 0.9, you will take average of last 10 entries. If your beta is 0.98, then you would be taking average of last 50 entries, and if you would take beta as 0.5, will average last 2 entries.
Yes, sir. And after averaging, will it result in the loss of some features or information?
Yeah, definitely. I mean, at instantaneous information, you would slightly lose out. You can lose out if, now that depends on your problem. If that
Yes.
is very important to you, yeah, you will. You
Yes.
see, you will, if you have this kind of oscillation, if you have this kind of a curve which has oscillations, and if you transform this to this kind of a smooth curve, then you are, from this curve you cannot tell the actual value, right?
Yes.
That existed at a particular iteration. So but we can tell like some mean value of the
Yes.
cost function. So yeah, definitely you will lose out on some information, but in cases where you would need to smoothen out your data, this is a very good strategy.
Yes, sir. Means in a broader sense, we can use this
Mhm.
technique uh, for making comparison and how it is working with.
Yes, 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 yes,
Yes, sir.
yes. Also, since I don't know, we are not interacting in a offline session, so please say your name before asking any question or talking, so I will understand who was there and who am I talking to. Okay.
Yes. Yes, sir.
Yeah. Yeah. Okay. So we will now go through Kera's. Last class we did beginner, quick start, and Keras basics. So we'll delete this from here. Now this time we will go to load data. Okay. So this tutorial provides examples of how you can use. So I think we left it here last time on how to use CSV data in TensorFlow. So are you guys going back and trying TensorFlow, or is it just that we are moving ahead and you are not doing anything at your end? Because if you like, I will be repeating a lot of stuff, but then if you don't practice, then like I don't think it makes sense, because that's the whole point of doing this exercise.
Yes,
Like,
sir.
yeah.
Yes, sir. Actually, what is happening? We are getting introduced to many new terms. So,
Hmm.
at a time means, so we are not getting the right point that on which particular platform we should start
Okay.
practicing.
So what you can do is, everybody has a Google account, right? So you can right away. So Google, as I already told, Google has this free service known as Google Colab, and it gives you a 16 GB. You can see I have a Colab Pro membership, but for with a free Colab account, you can get two options of RAM, and you have the GPU option from here, GPU and TPU. So even with a free Colab account, so these tutorials, this is the official TensorFlow tutorial. You have options to download, run it in Google Colab, view source on GitHub, and download the notebook. So the best method to learn is you run it in Google Colab with your Google account. Like that's it. Like these are end-to-end examples, and this is the best way and the only way to, like, not the only way, but like people spend a lot of money also these days learning these things from outside. But then the best possible method is to learn from, like, because they have made these things readily available, and these are really nice tutorials that they have set up.
Yes, sir. So, is it giving the
Hmm.
practical examples on a TensorFlow platform?
Yeah. See,
Yes, sir.
this is Collab, right?
Yes.
So you go here and then you click on run in Collab, and now this is using TensorFlow, right? So
Yes.
TensorFlow is a Python library
Yes.
which uses CUDA. So you, for running any model on GPUs, you would need CUDA, and TensorFlow has wrapped everything for you in Python. So you would not need to do anything of those CUDA programming or those dirty stuff on your own. They have given you everything. So what you would, but still there are a lot of syntax that you would need to be aware of. So which you should see. You guys must be aware of Jupyter notebooks, right?
Yes, sir. Jupyter
So
and
this
Spider.
is Collab is just Jupyter notebook. So you would have
Yes,
to
sir.
just press shift and enter, and you run this cell. So at least, if nothing but, at least run these notebooks at your end and see what is going on. That will give you a sense of like understanding, and it will make things much more clear to you.
Yes,
So in this example, yeah. So is there anybody else who has, or you? It was Priyanka, right?
yes, sir.
Yeah. So is there anybody else who has any question or comments? I can see Shubham that you are speaking, but you are muted. I don't know if you are speaking or you are talking to somebody else. Hmm. Okay. So in this notebook, we will look at how to load data off the disk and pre-processing it in the form suitable for training. So for any CSV dataset, the simplest way to train a TensorFlow model is to load it into the memory as pandas data frame, or as a numpy array, and relatively, so we are going to use this data set, which is, I think, yeah, this is where we left last time. So this is a data set of some kind of fish, which is we have got this, the table or the pandas data frame. So we have the columns length, diameter, height, whole weight, chunked weight, and the last column is age. So the problem is to predict the age of this shell from the different measurements. So the things that we have, the predictors or the precursors, these are the features, and the final variable that you have to predict is the label, or what we call also as the target. So we would extract the features and the labels. So you can see that so if we just print the head, you don't have the age column here, and if you just print the labels, so this is just the age. Okay, so what you have basically done is you have copied the entire training data. So what is your training data? So the training data has also got head. So you have put your entire training data into this ab alone features, and now from this ab alone features, what you do is you pop out age and assign it to labels. But once you do this, run this pop, this age column, it gets deleted from the original pandas data frame. Okay, so then we would treat all the features identically. So what they do is, so these numbers are already in looking like in the range of from 0 to 1, and you would make it into a numpy array, and then we can make a regression model to predict the age. So we can say that we will use in this one, they are first using the sequential framework or the sequential paradigm. So there are two, as I explained last time. One is the sequential, and then we have the functional programming in TensorFlow. So the hidden layer, so we have one hidden layer and then one output, which will be the age. So the hidden layer has got 64 nodes or 64 neurons, and okay, so this is your model, abalone model, and then you would compile your model. So the loss you are using is the mean squared error. So we are all aware of mean squared error. It is in the losses class. The optimizer that we are using is the Adam optimizer. So today we have discussed about Adam optimizer. uh, it is adaptive moment estimation, a combination of RMS prop and momentum. So you see, here we are not giving any values of the beta 1, beta 2, or epsilon terms. So there are some, by default, there are some values of these hyperparameters for the Adam optimizer that would be assigned in this case. So then what we would do is we would fit the model. So okay, so you can see that our loss, which is in the form of mean squared error. So it in the first step. So because we randomly initialize the weights, it was 69. It reduced to 6. Now you have seen the most basic way to train the model using CSV dataset. Next, you will learn how to apply pre-processing to normalize numeric columns. So it is so they say that it's a good practice to normalize the inputs to your model, and Kera's pre-processing layers provide a convenient way to build this normalization into your model. And the layer will pre-compute the mean and variance of each column, and then use these to normalize the data. So first you create the layer. So you see that you from at the time of uh, like importing. So you have imported the layers class from tensorflow.keras. So you would in the layers, so we have this normalization class. So we instantiate a normalize object of the normalization class, and then what you would do is you would use the normalization.adapt method to adapt the normalization layer to your data. So you use this only. Yeah, is there any question?
No, sir.
Are you guys able to see my screen?
Yes, sir.
Okay. So you would typically use the adapt function to basically run the normalization only on the training data. So he's only applying it over the input, so only over the features. So you say normalize.adapt abelon features. So then after this, then you use the normalization layer in your model. So the first thing that you do is, so you have normalization normalize here, then you say layers.dense 1. So you have the 64, you have the one hidden layer with 64 neurons, and then you have one output layer with one output unit, and then you would typically do the compilation, provide the loss function and the add optimizer, and then again if you run this model, so you can see that it has previously it was up to 6.5. Yeah, so it almost reached the same loss, but then like typically, so because I think that's because your values were already in the range 0 to 1. But if they are some large values or some very small values, then this would make a real difference. So like this loss would then typically be much larger than your loss after normalization. So then we would talk about the mixed data types. So they are talking about the Titanic data set, which contains information about the passengers on the Titanic, and the task here is to predict who survived. So we would first read the data set as a pandas data frame. So you can see that survived, there is a column survived. So 0 means that the person died on Titanic, 1 means that the person survived. And then we have the sex, age, number of siblings or spouses, the parch, I don't know what this variable is, what was the fare, the class, the deck, the embark town, whether the person was alone or not. So then we would separate the features from the labels. And since this data is having different data types and ranges, you can't simply stack the features in a NumPy and pass it to keras.sequential. And each column needs to be handled individually. So as an option, you can pre-process your data offline to convert categorical columns to numeric columns and then pass the pre-processed output to your TensorFlow model. There is a disadvantage to that approach, which is that if you save and export your model, the pre-processing is not saved with it. And Keras pre-processing layers avoid this problem because they are a part of the model. So Keras pre-processing is very useful in this case. And in this example, you will build a model that implements the pre-processing logic using Keras functional API. So you could also do it by subclassing, they say. And so we would create an input, symbolic input, which is from the Keras functional API, and then we would say that so result equal to 2 into input plus 1. What is the result? So for now everything is empty, and then you will perform you will use this calc, which is a kind of an object of this model. So you will build this model tf tensorflow.keras.model. What is the inputs, what are the outputs. So then you will pass the values so to this calc. So the values that you will pass will be the value of the input. Okay, so then you can see that if you print the numpy values, so it will print 2 into 1 plus 1, 2 into 2 plus 1. So then to build the pre-processing model, you have to start by building a set of symbolic keras.input objects matching the name and the data type of the CSV columns. So you see here we are having an input dictionary. So we are saying that for name, so I will first, so I hope you guys are comfortable with dictionaries, right? Yes, no?
Yes, sir.
Okay. So you can see that when we are iterating over the name and the column, so this will iterate over all the columns, and this will print the name and the column. So let me just turn off column. Yeah, so this is the This is the name of all the features, and if you would want to do this on the labels, so this will, I think, print only survived. Oh, what is this? Yeah, so this is looks like does not pandas data frame, so that is the reason. Yeah, it looks like it's a pandas data series. So what is Titanic features? Yeah, so this one is a pandas data frame. This is just a single series. Okay, so then you would say that, okay, so if your data type, you would see, so the column that from that particular column, you would iterate over all the columns, and if you are, so from a for a particular data frame, you would say dot items, so that so you can iterate over the name and the column values. So if the data type is, so you would compute the data type. If it is an object, you would make it into tf dot string. Otherwise you would make it into tf dot float. So basically what you are trying to do is, you are saying that if it is equal to object, if object data type, then you make it into string. Otherwise you turn it into numeric data type, and then you are creating a dictionary. So what your dictionary would here be is, it's a TensorFlow input. So you can we can see this input keras TensorFlow. So kf tf dot keras dot input. So you can see this input is used to instantiate a tensor, keras tensor, and a keras tensor is a symbolic tensor-like object which we augment with certain attributes that allow us to build a keras model just by knowing the inputs and the outputs of the model. So for instance, if A, B, and C are keras tensors, it becomes possible to do model equal to model, input equal to A comma B comma output equal to C. So basically A, or these numbers need to be the keras tensors, and input is used to instantiate a keras tensor. So you would, the way you would typically instantiate is, you would provide the shape or the size of the input, which is like, which it's like defining how you would define data type in Fortran or C or C++. So you are defining that particular variable. Yeah, so you would instantiate this as an input, so as a keras tensor, and okay, so that is what we are doing here. So the input with the value with the shape 1. So you are having, these are just one single values, so age and number of siblings, and these are the different number of different rows are the different number of samples or different number of examples. So then what you would typically do is, you would extract the numeric outputs. So you would say numeric outputs equal to name, and name colon input for name comma input in input dot items. So you have these inputs, you would iterate over this dictionary, and you would do this only if the input dot data type is tf dot float 32. And if you remember, for the numeric data types, we have forced them and provided them a tf.float data type. Now what you would do is you would say x is equal to layers dot concatenate, and you would list the, so you would create a list of all the values of the numeric inputs. So these are your so this becomes your input, and then you would typically do normalization. So we would create a norm object, and then we would say norm.adapt np.array, and then we would say Titanic numeric inputs dot keys. So if you would see, we will run this first, or we will run this in different cells. So you can see that numeric inputs. So you have these are your numeric inputs: age, fair, and siblings, parch. And if you print a particular, so in this dictionary, if you want to print a particular key,
Hello.
yeah,
Akaba.
hello, hello, am I audible?
Yes, sir.
Okay, boss.
Yes, sir.
Thank you.
I think somebody is
Yes,
yeah,
someone.
it looks like, yeah,
Yes, sir.
please switch off the mic because that is causing, yeah, okay. So you can see that we are so this is our this is our this is our dictionary with the keys. We have these as the keys, and these are the values. So we have a key value, we have key value pairs in the dictionary. Now what we would do is we would concatenate these layers. So we would see what it does. So we would say layers dot concatenate. So we would concatenate all these. So these are Keras tensors. All these are our Keras tensors, and we would concatenate all of them. So then this would correspond to 4 columns, and you have a series of rows. So all of them, all the rows are the different number of samples. So then we would start our normalization. So yeah, so also we would see what is the Titanic that he is referring to here. Titanic dot head. Yeah, so this Titanic is the original data frame that we had. So what we would do is we would run norm equal to, so we would create an object of the layers dot normalization, and then we would run it over all the keys. So what are these keys? Yeah, so you can see that these keys basically are the, yeah, so these keys are the all these name of the columns. And if you print and see what is the so if you would just select these particular columns from this data frame, and we will just print the head. So you would just get these 4 columns, and so this is what we are doing. And if you would say an np dot array of this data frame, then this will turn into a numpy array. So then we are saying norm dot adapt. So you basically run the normalization over these, and then you say all numeric inputs equal to norm of x. So you basically run the normalization over all the numerical inputs, and then what we would do is we would collect all the pre-processing results to concatenate them later. So we would say we would make a list of, we would say pre-processing inputs, equal to a list of all numeric inputs. And then for the string inputs, we would use tf.keras.layers string lookup function to map from the strings to integer indices in a vocabulary. So what you would typically do is, for example, these strings, third, first, uh, Cherbourg, Southampton. So you would turn them into some numbers or some integers so that we can train the model with with this information as well. And next, use category encoding. So we would do an encoding to convert the indices into a float 32 data appropriate for the model. And so the default setting is to create a one hot vector encoding, and a layer dot embedding would also work. Is like, so that's what they are saying. And so you would iterate over all the inputs. So what was our inputs? We would see, yeah. So this is our input. This is our input dictionary, and we would iterate over the key value pairs of this input. So we would say if the data type of that particular column is float. So we have already extracted the numeric values. So then you continue. So don't do anything. Otherwise, we would run this. So first is the lookup. So you would say you do string lookup vocabulary equal to np dot unique Titanic features name. So you can see that. So we would run this first, and we would say, let us say name here, and we would also let us also print lookup, and let us also print one hot. So you can see that the first column that it goes to, it is sex, and then we are running this lookup. So what this will do is it will print. So let us also print this one. What are the unique variable name? What are the unique names in the so in this column? I think one bracket is missing. So we can see that. So it is printing the column name, the unique names of the column in the column. So the column name, these are the unique names in the column. So then what it is doing is we are printing the lookup. So it is printing for us a string lookup object. So then this lookup is used as an input in the category encoding. So at that time, it's not printing one hot. Let me see. So it is basically printing. So we are also doing category encoding, and we are saying maximum tokens. So maximum number of tokens equal to lookup dot vocab size. So the size of vocabulary for the sex column is 2, for class is 3, for deck is 1 2 3 4 5 6 7 8, for this one is 8, for alone is 2. So we are making this one hot encoding. And then after that, what we would do is we would say x equal to lookup input. So this would first run lookup over over the input, and then x equal to one hot x. So this will run the one hot encoding over x. And let us, so this was, so these two commands, they were creating objects lookup and object of one hot. And we will see how after one hot encoding it looks like. So vocab size is deprecated. Please use vocabulary size. Okay. Vocabulary size. Max tokens is deprecated. Please use num tokens. Okay. So as you can see that we are printing the name, the unique values, or name of the table, name of the column, the unique values in each column, and then we are printing the one hot encoded vector. So in this one you can see that it is having a size 3, in this one it is having a size 4, in this one it is having a size 9. So it is having either, so one hot, yeah, we will just have a look at this. Why is it adding one more? Okay, so category encoding is a processing layer, pre-processing layer, which encodes integer features, and we can use it as tf.keras.layers, category encoding, number of tokens equal to what we want to give. And for example, if we give the number of tokens as 4, the output mode is one hot. So then if we give 3, 2, 0, 1, so for 3 it is giving us, yeah, so it is giving 0, 0, 1, 0, and then for 2, okay, no, for 0, for 1, okay, yeah, so yeah, sorry, it starts from 0. So 3 would be 0, 1, 2, 3. So this is 3, then this is 2, 0, 1, 2, then this is 0, and this is 1. So that is what it does, but I'll have to see why it is adding one more to the tokens, and number of token equal to this one dot lookup dot vocabulary size. So let us also print the vocabulary size. Okay, so we'll have to see why vocabulary size. Okay, anyways, so this is basically turning it into a one hot encoded vector. And then, so with the collection of inputs and pre-processed inputs, so we would append these one hot encoded vectors to the pre-processed inputs. So we would keep appending x to that, and so we would then concatenate all the pre-processing inputs. So we would say layers dot concatenate pre-processed inputs, and all these pre-processed inputs are Keras tensors. So then so then the Titanic pre-processing, it becomes tf.keras.model. So then we have the inputs and the pre-processed inputs with the categories. So yeah, so we were having the inputs. Yeah, so these were our inputs, and let us see our pre-processed inputs. So these are our pre-processed inputs, and then we would plot this model. So you can see that this model looks like something like this. So wherein you would have age none comma 1, none comma 1, and you have the different inputs, and then which are, so all this pre-processing and encoding, you can see all the things that we did in this example. of pre-processing. And then this model just contains it says input pre-processing. You can run it to see what it does to your data. Keras models don't automatically convert pandas data frame because it's not clear if it should be converted to one tensor or to a dictionary of tensor. So convert it to a dictionary of tensors. So let us do that. And so what this will give us is, so this was our Titanic features. Okay, let us print just the head. Okay, and so our Titanic features dictionary, it is, yeah, so this is our Titanic features dictionary. So these are the different actual dictionary in the pandas data frame converted to the dictionary. And he says that slice out first training example and pass it to the pre-processing model. You see the numeric features and string one hots all encoded together. So you would say the features dictionary is equal to name colon values. So values you just say up to colon 1 for name comma values in Titanic features dictionary dot dict, and you pass this to the pre-processing Titanic pre-processing that we created above. So you see here we created this Titanic pre-processing, which contains all the pre-processed inputs. And so this will have the features dictionary. And so this contains, just up to one value, and in the Titanic features dictionary. And if you print the shape of this, so yeah, already we can see it's 1,148. So this is the shape. So all the uh, one hot encoding, they have got elongated. So if we were having 001, that so all the threes, so all the single columns there become 3 columns or 5 columns or as many columns. So you can see that this becomes 3 columns, this becomes 4 columns, this becomes 9 columns, this becomes 5, then this becomes 3. and then you build the Titanic model, which contains the pre-processing head, and you have the input. So the body is basically contains the same thing. You have a hidden layer of 64 nodes, and you have a dense layer as output target, which is whether the person is alive or not. And then you pass the input to the pre-processing head. So you say that's the pre-processed input, and result, you say you pass the pre-processed input to the body, and this is the body model. And then you say our model is tf.keras.models input comma result, and then you compile it using a loss function known as binary cross entropy. So binary cross entropy, as we already discussed, is a loss function for categorical data sets, and it computes the cross entropy loss between true and predicted labels. So for example, you have y true as 0 1 0 0, and y pred is minus 18.6.51 2.94 minus 12.98. So this will basically compute your binary cross entropy. So in this case, we can see that our actually the predicted class is this one, class number 2, but the actual class is the class number 1. So this is the binary cross entropy loss. So we are using binary cross entropy loss, and then the optimizer is Adam, and then we return the model. So Titanic model equal to Titanic model. So this is the Titanic model function, and then we first pass the Titanic pre-processing comma inputs. So then you would run this model on the Titanic features dictionary and pass the Titanic labels. So you can see that the loss decreased. Now, if you want to see how your final Titanic features dictionary looks like, so we can print that again. Yeah, so this was our Titanic features dictionary. And so you see we are passing these things with the actual data set, and the pre-processing layer here in the function, it takes care of converting all these male female to the one hot encoding, and then you are passing the Titanic labels. So you would say, so these are the labels, and we run this for 10 epochs. So we can also save the model. So we can say Titanic model dot save test, and you can reload the model. So you can say tf dot keras dot models dot load model. This is taking some time, and okay, so this has been written, and so you can then also use tf.data. So tf.data is a specific data type of TensorFlow, which is, so they have this tf.data API, which is very useful for fast IO operations and putting the data on the GPU. So you should know about this, go and read about tf.data. And as a first example, so you can also convert your CSV data to tf dot sorry to tf dot data, and then we have the concept of data set. So I think we are already at 4 p.m. and this one has taken a lot of time, but I will leave this to you to go and explore this notebook more, and I will put this on the in the presentation, so you can just go and see this notebook at your end. So are there any questions?
Yes, sir. In the it's Priyanka.
Yeah, Priyanka.
In the code, that continue statement was there after if conditional statement if.
Okay, just a second. Continue. Okay, yeah, here.
In the third line.
Okay, yeah.
So after continue command, which line it will execute or where it will jump?
See what this will do is, so you enter the for loop, okay, and then you check the data type of input, okay. If that is float, then you would say continue, okay. If this is true, then continue will get executed and you would go to the next input, okay. If this is false, then this won't get executed, but the code will run. So these things would run.
Yes, sir. And okay. When data type is float, then it will go to continue and execute for statement.
Yeah, then no. So if data type is float, then it will run, continue will get executed, and then it won't run all these lines, okay. Then it would again go to the next input, like then it will okay, it will go to the next input, then again it will check whether it is float. If it is again float, then it will continue and go to the next input. It won't, so if it is float, it won't run all these statements.
Okay, sir. And for float statement, what it will indicate?
See, what we have done is, see, for float, for all the floats, we have already, if you see here, we have already made these pre-processed inputs, all the numeric inputs. We have already made them, right? age, number of siblings, parts, and fair.
Yes.
So that is what we are doing. So we have already pre-processed for the floats, and now we are doing pre-processing for the string
Okay.
columns.
Yes.
So
Means
yeah,
here
so
we
for
are
that,
filtering the floats for
yes, so that is
for
why
filtering
we
of
are
floats.
yes, so that is why we are not doing anything to the float, because for the float we have already prepared this all numeric inputs. So you can see that this one all numeric inputs, how it looks like. So it is already a Keras tensor. See, we have already this one all numeric input. We have already done the normalization as well, and we have done concatenation. Okay, and to the numeric inputs. And what was our numeric input? So numeric input was basically this dictionary with the keys and values, and the values were all Keras tensors.
Yes.
Okay. Yeah.
Yes.
So, is there any other question? Or Priyanka, you have any question? Further questions?
Yes, sir. That was the question because
Okay.
means what it will execute.
Mm-hmm. Okay. Is there any other question that you guys have? Shubham, can you please unmute your mic? It seems like you are not attending the class, but you are talking to somebody, and then you are just. Shubham, are you there? He's left the meeting.
Yes, sir. He's saying that his system is hanged right now.
Okay.
Yes.
So, is there any other question that you guys have? No.
Hello,